All right then, good day. Welcome to this video. So today I'm gonna do the intermolecular forces problem solving questions as you see here on the screen. So let us go through the whole question. And remember, also I try to employ the basics so that you can understand why do I solve these, how do I solve these questions, okay? So now let us start by reading first. They say to us, we are given the table, we are provided with the table. The table below shows the boiling point, okay? We are given the boiling points, shows the boiling points of the hydrides of group 4, compounds in which hydrogen is bonded to elements from group 4 in the periodic table, okay? So these are 1, 2, 3, 4. 4 hydrides. Okay, we call them the 4 hydrides. Why do we call them? Because these compounds are compounds made of hydrogen atoms and group 4 elements. So when you go back to your periodic table, you will see that the hydrides, let me go to my periodic table. When I go to my periodic table, I have group 4 elements. Okay, so these all group 4 elements that we are going to talk about: the carbon, the silicon, germanium, and the tin. All of these 4 elements, when they react with hydrogen atoms, they form what you call the hydrides, okay? So now here, these are 4 hydrides they are talking about with different boiling points, with different relative molecular masses, most definitely. So according to this table, or based on this table, we can see that moving down the table, the boiling point is actually increasing. Meaning in this case, CH4 and SNH4, they have distinct boiling points. The boiling points of SNH4 is much more higher than the boiling point of CH4. Here we're talking about the less boiling point, and then here we're talking about high boiling point. Now, this boiling point, for it to be this distinct, it's because of certain characteristics that are found in these compounds. Now, this compound compared to the last compound, they are most definitely not the same due to the fact that their relative molecular masses are not the same. There could be common things that are found in all of these hydrides, but there is something different about them, which is their relative molecular mass. So based on the relative molecular mass, we can simply conclude that this is one of the reasons why the boiling point is also not the same. So now when I move down the table, the relative mass does also increases. So the more we have, the greater relative molecular mass, the more the compounds need more forces to be broken down. So because here we are talking about the intermolecular forces, we're going to talk about the forces that are acting, or the forces that are taking place in all of these compounds. Now let us talk about those forces. Now, if you look at these 4 compounds, they have one type of a common intermolecular force. The common intermolecular force, it is called induced dipole force. So CH4, SiH4, GeH4, SnH4, they have a type of intermolecular force which we call induced dipole dipole force. Okay, there's this type of intermolecular force. So induced dipole force, it's a type of a force that will get within the molecule of these hydrides. That means if I take CH4 to CH4, I take SiH4 to H4, and I take GeH4 to GeH4, SnH4 to SH4. This type of a force that will exist between these 2 molecules, we're gonna call it induced dipole force, or mutual induced dipole force, okay? So it exists within these two molecules. So now in this case, there are different types of intermolecular forces. We have induced dipole force, we have dipole force, we have dipole force, we have hydrogen bond, which is the greatest of them all, type of intermolecular force. So induced dipole force, amongst the van der Waals forces, it is the weakest of them all. So now this is what I want you to take note of. Like I said, all of these hydrides, they have the same type of intermolecular force. But then while their boiling points are different, whereas they have the same type of intermolecular force, you would most definitely expect the boiling points to be the same, since well, they have the same intermolecular force. Therefore, the factor that influences the boiling point not to be the same, it is the relative molecular mass, like I said. So that means the higher molecular mass, the more intermolecular force we get. So that means induced dipole force of SNH4 will take place at greater points or many points than induced dipole force at CH4. So hence why we say the induced dipole force that will take place here, it will be much more greater than induced dipole force that will take place at CH4. Not that they are not the same, they are the same. It's just that here we have more relative molecular mass compared to there. So that means here we need more. It's like here we have one guy and then here we have 5 guys. So in order for me to overcome 5 guys, I need 5 intermolecular forces. Here I have one guy. In order for me to overcome one guy, I need 1 intermolecular force, which is induced dipole force. You see? So here we need more induced dipole force, and here we need less induced dipole force. Okay? So that's why here we have higher boiling point. So now let us go through the questions. So 3.1, it says to us, what is the phase? Is it solid, or is it liquid, or is it gas of the hydrides above 25 degrees Celsius? Okay, so these hydrides, these are their standard temperatures in terms of the boiling points, okay? So as you look at these temperatures, they are all negative, but immediately when we introduce positive temperature to these hydrides, what is going to happen? What will be the phase of these hydrides? Most definitely, it will be gaseous state, because remember, these are the boiling points. So in order for CH4 to boil, you need a temperature of negative 164 degrees Celsius. So that means for it to boil, it will change its state. Maybe if it was in in liquid state, it will automatically change to gaseous state, because this is because here we're talking about the boiling point. Okay, we're not talking about the melting point. Melting point, it's when maybe it's a temperature at which a substance will change its state from solid to liquid. That's a melting point. But boiling point is a temperature at which a substance will change from liquid to gas. So that means CH4, for it to change from liquid to gas, you need negative 64 degrees Celsius. Same applies with SNH4. SNH4, for it to change from liquid to gas, that means for SNH4 to boil, we need a temperature of 52 degrees Celsius. That means when you introduce a positive temperature like this one, so what will be the state of all of these hydrides? Most definitely will be in gaseous state. Gaseous state, because this is extreme temperature for these hydrides to boil. So that means to answer question number 3.1, where they say what is the phase, solid, liquid, or gas of the hydrides above at 25 degrees Celsius, it's going to be in gaseous state. So that means here we are looking at gas. Okay, so that's how we answer 3.1 in this case. Now 3.2, it says to us, name the type of what? Of van der Waals forces between molecules of the hydrides in the table below. Above. Remember, what did I say to you? I said the intermolecular force of all of these 4 hydrides, it is the same. So what is the name of this intermolecular force of these hydrides? We're going to call them induced dipole force. You can say induced dipole force, okay? Or you can just simply say induced dipole force, okay? So now that means it is induced, or London force. It is induced dipole force, induced dipole force. It's mutual, okay? So it is induced dipole force, induced dipole force. So you can just write induced dipole force. Now 3.3, it says to us, explain the trend in boiling points observed for the hydrides in the above table. In your explanation, refer to molecular size, very important, molecular size, intermolecular forces, and the energy needed. Okay, so that means when we do our explanation should entail these points that they have mentioned in order for us to get 3 marks. Okay, so we're going to talk about the trend of the boiling points observed. Now, this is what is happening. It's up to you. It's either you're going to move up the table or you're going to move down the table. So I prefer to move down the table since well I indicated with this arrow. So that means from CH4 to SNH4, what is happening with boiling point? Boiling point is most definitely increasing, right? So we're going to explain that. Why is boiling point increasing from CH4 to SNH4? We're going to explain that referring to molecular size, intermolecular force, and the energy needed. So I'm going to start by talking about the intermolecular size, okay? So why is boiling point of these hydrides increasing, moving down the table from this position to that position? This is one of the reasons based on the molecular size. Number one, the relative molecular size of the hydrides moving from CH4 to SNH4 increases. Therefore, as molecular size increases or due to increase in molecular size, more energy is needed. I think I'm going to need this before this one, okay? So more energy is needed to overcome the strength of intermolecular forces amongst these hydrides compounds, okay? So that means, let me try to write it down. I'll explain it much more better if maybe so that it can make sense. So like I said, I'm going to start with molecular size, meaning why is boiling point increasing from here to here? So that means I'm going to say from CH4 to SNH4. What is happening? The molecular, the relative or molecular, the molecular mass of hydrides or compounds, you can say of hydrides increases, okay? Increases. That's the first mark, increases. Therefore, more energy is what? Is needed. Is needed to do what? To overcome the resulting increase in what? In intermolecular force. Or you can simply say, instead of saying intermolecular force, you can say the resulting, to overcome the resulting increase in, instead of saying intermolecular force, here you can say induced dipole force, okay? So now let's try to break this down, okay? So from CH4 to SNH4, the molecular mass is increasing, right? As the molecular mass increases, that is the strength of intermolecular force does also increases. So that means why the strength of intermolecular forces increases is because we needed more energy to overcome that strength of intermolecular force of these hydrides as we move down the table. So hence why I'm saying to you, the molecular mass of hydrides increases, and therefore more energy is needed to do what? To overcome the resulting increase in intermolecular force. So this increase in intermolecular force was made by the increase in relative molecular mass. Okay, so that means this is how we answer this question. We're not going to mention the boiling point. We want to know why the boiling point is increasing. So this is the reason why the boiling point of our hydrides moving down the table is increasing. Okay, so that's how we answer 3.3. Therefore, we move to the second question. So the statement here, it says to us, the graph below shows the boiling points of the hydrides of group what? Of group, now it's group 6 in the periodic table. This is their relative molecular mass, okay? So now what is happening is that we can see from our periodic table, now we are talking about group 6 elements, okay? These are group 6 elements, okay? So they're going to react once more again with hydrogen atoms to form the hydrides. So that means oxygen, sulfur, selenium, and tellurium. They're going to react with hydrogen atoms to form what? To form what you call the hydrides, okay? So now in this case, to answer this question, let's have a look. Now we are given our information in terms of our graph. Remember here it was given in a form of table. So now it is given in a form of a graph, okay? So now the graph of boiling point versus relative molecular mass. So here the variables are the same, but the presentation, it is not the same. Here it is given in a form of graph, okay? So learn how to analyze the table, also learn how to analyze the graph. So we are also given the relative molecular mass as well as the boiling point, okay? So now from this graph, let us try to answer the questions. So from the graph above, the juice, and then write down the name of the hydride. That is, start with 3.4.1, okay? 3.4.1. Hydride with the weakest intermolecular force. So which hydride in this graph has the weakest intermolecular force? The hydride that has the weakest intermolecular force, it has a very extreme, compared to others, it has a very extreme low boiling point. So that means in this case, this is the lowest peak of our graph. So that means hydrogen sulfide, or H2S in this case, it is the hydride that has the lowest boiling point amongst or compared to the other hydrides. So for a fact that H2S has the lowest boiling point, that means it has the weakest intermolecular force of them all, okay? So that means the question, it say to us from the graph above, the juice and then write down the name, it didn't say the formula, it says the name of the hydride with the weakest intermolecular force. So what is the name of H2S? The name of H2S is going to be hydrogen sulfide, okay? Hydrogen sulfide, okay? It's hydrogen sulfide. I have learned that you can also write this as F, okay? Sulfide, okay? It's still correct. Therefore, 3.4.2, it says to us, again, give the name of the, from the table, from the graph above, give the name of the hydride with hydrogen bonds between molecules. So now, so far, the type of intermolecular force that we've discussed on this question is induced dipole force. So here now, they are asking us about the hydrogen bond. So hydrogen bond is one of the type of intermolecular force that we can also talk about. But you have to bear in mind that the hydrogen bond is one of the strongest of intermolecular forces that you'll ever have. So it is not that easy to break the molecules that has this type of bond, which is called the hydrogen bond. Okay, so now in this case, they want us to talk about the name of hydride on this graph that has a hydrogen bond. So remember, this is what I normally used to say. So now when you talk about the hydrogen bond, I normally say it's when hydrogen reacts with one of NOF. I call it like this, is NOF, okay? This is my NOF, okay? NOF. N for nitrogen, O for oxygen, F for fluorine atom, okay? So when hydrogen reacts with nitrogen, or when hydrogen bond with oxygen, or when hydrogen bonds with fluorine. So this is what you call the hydrogen bond. But do not forget, this is supposed to be between the molecules because we are talking about the intermolecular force, not intramolecular force or not interatomic force. So this is a presentation just to show you when I talk about the hydrogen bond, what am I actually talking about? So it's not between the atoms, it's not inside the molecule, it's supposed to be between the molecules, okay? So don't confuse that. So now in this case, if I take, let's say for an example, in even, how would you see a compound or a hydride that has the hydrogen bond? It has the highest boiling point because it has the strongest intermolecular force. So amongst these, so let's have a look at water. Water, it has the highest boiling point compared to all of these hydrides. So that means for a fact that means this, it's a hydrogen bond in this table, okay? This is a water molecule. So that means if I take water molecule to water molecule, a type of intermolecular force that I will get between those two water molecules will be called the hydrogen bond. So that means water is the one that has, and remember, they want us to write down the name. So we're going to say it's water. Don't write the chemical formula. You'll get it wrong because you didn't answer the question if you write it like that. So you can call it water or you can call it hydrogen oxide, okay? Water or hydrogen oxide. Therefore, 3.4.3, it says to us the name of hydride on this graph that requires the most energy to undergo a phase change. So remember, these are the temperatures for these hydrides to undergo a phase change. These are the boiling points, temperatures. So that means in this case, we would assume that these hydrides are in liquid state. So immediately when you expose them under these temperatures that are given for them, therefore they will start to change from liquid to gas because we are talking about the boiling point. So the question here, it wants us to determine the name of the hydride that requires most energy to undergo a phase change. So in this case, I have already talked about it. I said the hydride that has the highest boiling point, it requires the stronger intermolecular force. So as it requires the stronger intermolecular force, that means it needs more energy so that the molecules can be broken down of that hydride. So in this case, what is the name of that hydride for 3.4.3? It's going to be water once more. Again, it's going to be water. Okay, so that will be 3.4.3. Now for 3.5, it says to us, refer to intermolecular forces. Okay, refer to intermolecular forces and energy and give a reason why one of the hydrides of group 6 deviates from the trend in boiling point observed for the others. Now, this is what is happening. To answer 3.5, now, water is one of the hydrides that deviates from all of these hydrides. You can even look that all of these hydrides, it's either they are on the x-axis or below x-axis. Only water, it is above the x-axis. Okay, and then water is the one that has the highest, which is 100 degrees Celsius. It is the one that has the highest boiling point. So why is this? This is more like when we are asked to determine the scatter plot of this is an outlier. So we want to explain that reason why is water an outlier from this set of data. Okay, so now this is one of the reasons. And when we explain why water is an outlier or deviates from these other hydrides, when we give the explanation, You're going to refer to the intermolecular force that water experiences, because this is what is happening. All of these hydrides, they have the same or common intermolecular force. But water has two types of intermolecular force, including the intermolecular force that these experiences. But let's talk about the distinct one. Water has the hydrogen bond we have already talked about, and therefore these hydrides, they have what type of intermolecular force that we can talk about? They have London, they have, let me see, it's TT, they have the type of intermolecular force that you're gonna get here, it's dipole force. Okay. So now, for a fact that here we have dipole force, and then here we have the dipole force is not that stronger than hydrogen bond. Hydrogen bond is the strongest of them all, like I say. So that means you're gonna say the intermolecular force experienced by water, most definitely it's gonna be greater than intermolecular force experienced by these three. Number one. Number two, we're gonna refer to the energy. So that means for us, for water to change its state, we need more energy due to the greater strength of intermolecular force compared to these three. Okay. And therefore, now we'll understand why this water deviates that much in terms of its boiling point. Okay. So now to answer this simpler, we're gonna say water, or you can say H2O. Okay. The H2O molecule, H2O, has the greater boiling point than other three hydrides. Okay. Now, what is the reason behind that? So it deviates. We are talking about the deviation here. It's water that has the greater boiling point than other hydrides. So that's a deviation part that we are mentioning, that we are stating there. Okay. Therefore, water has a greater intermolecular force named hydrogen bond than other three hydrides. Okay. Therefore, water needs more energy to overcome the strength of intermolecular force. Okay, so this is one of the major reasons. Okay, so that means more energy is needed to overcome the strength of intermolecular force. Therefore, I hope everything was making sense to these questions. Till we meet once more again. Don't forget to comment, subscribe, and share with the friends.